Myra Butler, a recent graduate from medicine and currently completing my Master's of Health Science in Clinical Epidemiology at UBC. Today we're going to be looking at some different outcome measures. This video will consider the purpose of measurement, some options for measuring, and how to choose an appropriate measure. One of my professors this year told us, "What gets measured gets done," and I have found this to be very true. In this era of evidence-based medicine, a well-designed study, or even simple surveillance, can be a powerful tool for change. So choose your outcome wisely, since it will drive your study. At a more fundamental level, be careful what you choose to study in the first place. My father's advice is, never ask a question, or do a test, or a research study you don't want to know the answer to. Consider carefully the broader purpose of your study and how it will impact both patients and future research. It is also important to consider the clinical or practical importance from the beginning of a study. Be sure to pay attention to the difference between clinical and statistical significance. Let's get down to the practical side now. How do we measure? You can always measure the difference between groups, but the best method of measurement includes an accurate baseline measurement, followed by one or more measurements after the exposure. You can measure the amount of change, or you can also measure the rate of change. In the Introduction to Epidemiology video, we learned how to distinguish between outcome and exposure variables. Variables come in many different types. The first question is whether a variable is continuous or categorical. If it's categorical, is it nominal, ordinal, or dichotomous? A continuous variable can take on many different values, like a number line. The variable could take on the value of 12, or -3, or 0.01483. The possibilities are endless. A categorical variable, on the other hand, can only take on a specific set of values defined by its categories. There are two types of categorical variables, ordinal and nominal. The categories of an ordinal categorical variable have an inherent order, for example, age categories. Child is younger than adolescent, is younger than adult, is younger than senior. If the child category is defined as 0 to 12, then both a 2-year-old and an 11-year-old would be in that category. As you can see, when changing a continuous variable, like age, into a categorical variable, like age categories, it's very likely that you will lose information that may be important. A nominal categorical variable has no inherent order to it. For example, there are two types of trees, deciduous and coniferous. There's no natural order to these categories. A special type of categorical variable is a binary variable. This is when you have a categorical variable with two levels or categories, which are mutually exclusive. The clearest example of this is the outcome of death. A person is either dead or alive. There's no overlap between these categories, and there is no third option. The choice of outcome measure will depend on the types of variables you have and the study design. Regression is generally preferred for its ability to give an adjusted measure of effect. Use linear regression for continuous and logistic regression for binary outcomes. More on this later. Check with a statistician at the design phase of your study to determine the most appropriate measure and/or statistical test for your study. Binary outcomes are a special case and have many ways of being measured. The types of measurement include prevalence, incidence or risk, risk difference or attributable risk or absolute risk reduction, relative risk or risk ratio, and an odds ratio. Prevalence and incidence are covered in the Introduction to Epidemiology video. Here, we will concentrate on the last three. The results of studies with binary outcomes and exposures are generally presented in a 2x2 table like this. Although you can set up the table many ways, this is the conventional way of doing so. If you set up the 2x2 differently, remember that the little ABCD letters in the formulae will not correspond properly. The risk difference, also called the absolute risk reduction and the attributable risk, you simply subtract the incidence of the outcome in the unexposed group from the incidence of the outcome in the exposed group, as seen here. When you take the reciprocal of the risk difference, you get the number needed to treat, or the number needed to harm, depending on the type of situation. This is a very useful number in a clinical setting. Let's take an example where the baseline risk is 30% and the risk in the treatment or exposed group is 15%. By subtracting these incidences, you come up with a risk difference of 15%. In English, this means that treating patients resulted in a 15% drop in the risk of the outcome. When you take the reciprocal of 15%, or 0.15, you get 6.666. So for every 7 patients treated, 1 outcome event will be avoided. The next measure is relative risk, also known as relative risk reduction or the risk ratio. Instead of subtracting the incidences from each other, you create a ratio by dividing them. By convention, it's usually the incidence of the exposed divided by the incidence of those not exposed, but sometimes it's reversed, so pay attention to wording. Let's take that same example. In this case, the relative risk is 0.5 or 50%. In English, the treated group has half the risk of the untreated group, or the treated group has 0.5 times the risk of the untreated group. You could also say that the risk of the outcome for those without treatment is 2 times the risk of those who were treated. In general, if the relative risk is above 1, the risk of the outcome is higher. If it is lower than 1, the risk is lower, which can also be called a protective effect. Let's compare these first 2 measures. It's important to consider baseline risk. In this example, with a relative risk of 2, looking at the relative risk alone might suggest that this is a very important exposure. However, when you consider the fact that there is only a 1% change in the absolute risk, it becomes less clear whether this is a clinically significant exposure. Odds are a different measure of risk that is less intuitive except to hardcore gamblers or statisticians. An odds ratio is either the odds of an outcome with exposure divided by the odds of the outcome without the exposure, or the odds of exposure with the outcome divided by the odds of exposure without the outcome. Whichever way around, you end up with the same expression, A times D divided by B times C. The difficult part of an odds ratio is its interpretation. If we use the same example as before, we come out with an odds ratio of 0.4 or 2.4 depending on which way around it is. In English, the odds of the outcome with treatment are 0.4 times the odds of the outcome without treatment, or the odds of the outcome for those without treatment are 2.4 times the odds of the outcome for those with treatment. For most patients and clinicians alike, the last sentence was close to meaningless. In general, however, like the relative risk, if the odds ratio is above 1, the risk of the outcome is greater, while an odds ratio between 0 and 1 represents a lower risk of the outcome. As a side note, relative risks and odds ratios should always be a positive number. If a paper reports a negative relative risk or odds ratio, they have a mistake somewhere in their math. If you read much of the literature, you might find it confusing that odds ratios are sometimes interpreted as though they were relative risks. As we just saw, relative risk and odds ratios are distinct measures. There's one special case, however, where they can approximate each other. When the event rate of the outcome is low. Then the contribution of A and C to the denominator of the relative risk is overshadowed by the contribution of B and D, so that the relative risk is approximately equal to A divided by B divided by C divided by D, which rearranged is actually the same as an odds ratio. As you can see from this graph, as the baseline risk or baseline event rate increases, and with higher odds ratios, the relative risk is no longer approximated by the odds ratio. At low baseline risk, the odds ratio barely overestimates the relative risk at all. But by the time you get to a baseline risk of 50%, the odds ratio overestimates the relative risk by 100%. The rule of thumb is that the odds ratio is approximately the same as the risk ratio when the baseline risk is less than 5 to 10%. This is an important thing to keep in mind as you read the literature. It's extremely common for authors to misinterpret their odds ratio results as though they were a relative risk. When you see it, make sure the assumption of low baseline risk is met. Now let's consider which measures are useful in specific settings. A risk difference tends to be the clinician's measure of choice. It gives a sense of the absolute change in the risk and can be used to calculate the clinically relevant number needed to treat. Researchers, on the other hand, find this number cumbersome since every level of baseline risk requires a different risk difference, not to mention the fact that case control trials and exposure-based cohort trials are not able to produce such numbers. Researchers tend to prefer the parsimonious and easily interpretable relative risk. However, as we saw earlier, the relative risk may suggest a large effect despite a clinically insignificant change. Also, case control and exposure-based cohort studies can't produce a relative risk either. Lastly, there's this problem of the ceiling effect. First, let's compare the absolute risk difference with the relative risk, with the example of deep vein thrombosis risk for oral contraceptive users. The risk of DVT formation for smokers compared to non-smokers is constant. Let's say, for example, a relative risk of 2. The risk difference, however, changes significantly between age groups. For age group 1, the risk difference may not be clinically significant. However, by the time you get to age group 4, the risk difference between groups is almost certainly significant, clinically speaking. While the relative risk can be reported as a single number, a very attractive option to researchers with a word limit, in this case, the table of risk differences by age category is much more useful in determining clinical significance. So what is this ceiling effect? Let's consider when the baseline risk of the outcome is high. The maximum relative risk is constrained by the fact that the maximum possible risk in the exposed group is 100%. So if you have a baseline risk of 50%, what's the maximum possible relative risk? So let's assume the worst case scenario of 100% risk for the numerator, that is those exposed, and fill in the denominator with the baseline risk. That gives us a maximum possible relative risk of 2. In other words, even if the exposure triples the risk of the outcome, the relative risk would not be able to show the extent of that risk increase because it cannot get higher than 2. An odds ratio has some significant advantage. Unlike the relative risk, it has no ceiling effect, and you can always get them from case control and cohort studies. Also, you can calculate an odds ratio from a logistic regression model. The major disadvantage is that an odds ratio is difficult to interpret, especially when the baseline risk is high and the odds ratio does not equate to a relative risk. Let's take an example to compare these measures. In this example, the risk difference is 0.3, or 30%. In English, the risk of the outcome is 30% less in the non-exposed group. The relative risk is 1.75, or the risk of the outcome is 1.75 times greater in the exposed group compared to the unexposed group. Note that the maximum relative risk in this case is 2.5, so it's getting close to the ceiling and may be artificially low. The odds ratio is 3.5, which means the odds of the outcome given exposure is 3.5 the odds of the outcome without exposure. Remember, outcome variable type drives the type of analysis and regression you choose for your study. In general, use risk difference for clinical situations, relative risk for research situations, and odds ratios when the event rate is high or with case control and cohort studies, remembering that odds ratios are not the same as the relative risk when the event rate is high. Here's a summary of the formulae and their interpretations for future reference. It's also available as a PDF. The main concepts for this video were drawn from Dr. K.S. Joseph's Epidemiological Methods 2 course at University of British Columbia's School of Population and Public Health. Thank you for your time and attention.